In this lecture, we'll learn about the biocompatibility of alumina and carbon nanotube reinforced hydroxyapatite. We'll also learn the need for reinforcing alumina and carbon nanotube in a biocompatible hydroxyapatite. As we have learned in the earlier lectures that hydroxyapatite is one of the bioactive materials. So, but again the problem is it is highly brittle. So that is the reason we want to reinforce it with some other materials such as nanoalumina or submicron alumina, and also with carbon nanotube in order to see whether it can support or it can enhance the fracture toughness of brittle hydroxyapatite. At the same time, we want to maintain its biocompatibility. So we also need to verify that the material is again biocompatible or cytocompatible, and it is not inducing any toxicity once it is being implanted into the body. So in this particular lecture, we will learn about the biocompatibility and the need of alumina and carbon nanotube reinforced hydroxyapatite. Hydroxyapatite is one of the very well known biocompatible materials because its calcium by phosphate ratio is 1.67, which is similar to that of bone and teeth. So that is the reason it has been chosen as a matrix for a biocompatible material. Later on, this particular material has been spark plasma sintered. So in this case, we will talk about the processing part. So this particular material has been spark plasma sintered with the reinforcements of aluminum oxide and carbon nanotube to form a nano biocomposite. And why we are doing that, we will come back to the need of it. And then it has been a molecular modeling has been performed for the hydroxyapatite with carbon nanotube interface, because it is carbon nanotube which is imparting much fracture toughness to this particular composite. So we want to see what is happening at the interface between hydroxyapatite and carbon nanotube, and followed by cytocompatibility of the overall composite, overall biocomposite, whether we are able to retain the biocompatible nature of the hydroxyapatite even after reinforcing it with aluminum oxide and carbon nanotube. The biocompatibility of hydroxyapatite can't be understated. It is a highly biocompatible material. It has a chemical nature similar to that of bone and teeth because its calcium by phosphate ratio is approximately 1.67, which is found naturally in apatites. And again, depending on what its microstructure is, what is crystallinity and what is composition, it can highly affect the properties of a composite. So we need to basically control and retain the initial ingredients of hydroxyapatite in terms of its crystallinity, in terms of its microstructure, in terms of its composition, and without altering them, we should be able to tap it in the final implant material what we synthesize. But the problem, basic problem is hydroxyapatite is its highly brittle nature. Its fracture toughness is less than 1 megapascal root meter. It is highly brittle. So we need to somehow enhance its fracture toughness properties. So for that, we have couple of choices. So in first case, what we are doing, we are adding aluminum oxide. And since also one more advantage to adding aluminum oxide is it has a better wear resistance. And apart from its higher fracture toughness, it also have better tribological properties in comparison to that of hydroxyapatite. So on one hand, we are improving its fracture toughness because aluminum oxide has a better fracture toughness to the order of 3.2 megapascal root meter. At the same time, it is highly wear resistant because it also has very high hardness. So combination of high hardness and high fracture toughness, it can impart superior properties to hydroxyapatite. But the problem with this aluminum oxide is that it is bioinert in nature. It won't assist the precipitation of apatite on its surface. So that is the reason we want to add this particular material, though we know it is bioinert. At the same time, we want to make sure that this bioinertness of aluminum oxide should not interfere with the bioactivity of hydroxyapatite. So in this particular case, we are adding aluminum oxide as a secondary addition to enhance its wear resistance, at the same time improve its fracture toughness, despite it being the bioinert in nature. So we just want to make a nice complementary composite that I add certain percent of hydroxyapatite plus certain amount of aluminum oxide, so I get better properties, better mechanical properties, but without deteriorating its cytocompatibility. Further, there have been some studies which have also induced some carbon nanotube addition, some carbon nanotube reinforcement to improve its fracture toughness, and it has also been proved that carbon nanotube assists cell precipitation or the apatite precipitation on its surface. At the same time, it is improving its bend strength, improving the fracture toughness, but toxicity is always a concern because carbon nanotube have diameter to the order of 40 to 70 nanometer, less than 100 nanometers. So it can always induce some toxicity. It can even cause inflammation. They can get accumulated at certain locations. liver, brain anywhere else. So that's always a problem, that anything nano, once it is in body, it might create some problem. But there also had been a second school of thoughts which says carbon nanotube is a form of carbon, and carbon is the basic form of life, so why it should be a problem at all. So there had been certain concerns, but once we are able to trap those carbon nanotubes in a certain matrix of hydroxyapatite, we can somehow tap its bioactivity, at the same time not letting it become toxic or get loosed into the body stream, and thereby lead to its agglomeration at certain body or at certain organ location. So in this particular case, just to check how we can induce aluminum oxide and carbon nanotube, couple of methodologies or powder treatments have been done. So coming to the first powder treatment, nano hydroxyapatite has been taken. It has now been agglomerated to form hydroxyapatite or nano or agglomerated hydroxyapatite to get better flow properties. In second case, they have been blended with micron size aluminum oxide. So we are getting an agglomerate of hydroxyapatite, which is now some micron size aluminum oxide. Because if you want to disperse somehow aluminum oxide, if you want to disperse aluminum oxide into hydroxyapatite, we need to have it controlled in a very controlled fashion. And if we already have an agglomerate of hydroxyapatite, then it basically aluminum oxide just will disperse on the surface of hydroxyapatite, that also of an agglomerate. So if in case we want to blend them together and then do the spray drying, that might result much better properties. That's what is being done in this particular case, that aluminum oxide has been now blended with the spray dried hydroxyapatite. And in second case, we also want to disperse carbon nanotube, because carbon nanotubes are the one or the entities which can impart very high fracture toughness. So they have been first of all dispersed in an aluminum oxide matrix. So we get an agglomerate of aluminum oxide plus some carbon nanotube, and now those have been blended with the hydroxyapatite powder. So we have basically three cases. First, we have only hydroxyapatite without any addition. In second case, we have hydroxyapatite plus reinforcement of aluminum oxide. So we have blended the spray dried hydroxyapatite powder with the aluminum oxide powder. So in this case, we don't have any CNT. So from this particular combination, we can compare it with hydroxyapatite and we can see what is the role of aluminum oxide only to impart pressure toughness or improve its wear properties. So from jump from one hydroxyapatite to hydroxyapatite with some alumina, we can comment what is the role of alumina in terms of increasing its wear properties or wear tribology or improving its fracture toughness. In the second case, we have both. We have hydroxyapatite plus some alumina plus some carbon nanotube. So in this particular case, we can see what is the role of carbon nanotube in terms of improving its fracture toughness or wear resistance. So in that particular manner, we can compare these three composites. At the same time, once we are improving some property, some mechanical property, we want to make sure that they still remain cytocompatible or biocompatible even after the reinforcements of nano or submicron alumina and nano carbon nanotubes. So that is the overall strategy of doing the powder treatment in terms of evaluating what is the role of alumina and what is the role of carbon nanotube in terms of affecting the hydroxyapatite mechanical properties. So we have taken powder feedstock, which is of hydroxyapatite. Hydroxyapatite, though its size is different, it's in order of a couple of nanometers. It has been agglomerated as between 10 to 50 micrometers. So initially we have fine hydroxyapatite powders. Those have been agglomerated as a powder particle, which is again 50 to 45 micrometer in size. So we see something like this, 10 to 50 micrometer in size. So it's an agglomerate, and which has some nano hydroxyapatite available in it. In the second case, we have added some aluminum oxide. Aluminum oxide, again it is a spray dried agglomerate. So again we see an agglomerate, but now they both have been blended in the second case. So this is our first case, we only take hydroxyapatite. This is the second case where we have hydroxyapatite plus some aluminum oxide. So in this case we have blended them together to see what is the effect of aluminum oxide out there, and again we have formulated it in to the order of 10 to 50 micrometer in size. And the third case, some carbon nanotubes have been added. So we see the terminology hydroxyapatite and hydroxyapatite plus some alumina, it has been denoted by HAA, And once we also add some carbon nanotube, in this case it is 1.6 weight% carbon nanotube. So we denote it as hydroxyapatite alumina with 1.6 or 16 C, 1.6 weight% carbon nanotube. And carbon nanotube, as we know, they are the nano entities. So they have the diameter of 40 to 70 nanometer and a length of 0.5 to 2 microns. So from the combination of these three, we can always assimilate the data, and we can find out what is happening in terms of their contribution in terms of enhancing its wear resistance or cytocompatibility or even changing the fracture toughness. But one more part which was very critical out here is we want to disperse the carbon nanotubes, because carbon nanotubes, they have such high or superior mechanical properties. They have Young's modulus, elastic modulus to the order of 1.4 terapascals, fracture strength of 1 to 2 gigapascals. At the same time, they are very light. They are 1/6 as heavy as steel. So if we can somehow disperse carbon nanotube, we can achieve very uniform properties throughout the implant material. So somehow we want to disperse carbon nanotubes, but owing to their nano nature, they always have tendency to agglomerate because of their high specific surface area. They always have tendency to agglomerate and become some sort of micron size cluster. But once we have dispersed the carbon nanotube, once we have blended them in the hydroxyapatite matrix, it has been observed that these carbon nanotubes, they somehow disperse automatically. So we can see the cluster of carbon nanotube around this region. This is already dispersed. So this is again dispersed already in the hydroxyapatite matrix. These are nothing but hydroxyapatite crystals or powder particles. So we have hydroxyapatite powder particles, and we can see CNTs how nicely they have dispersed either on the surface, on their surfaces. And this is a zoomed up picture to show that CNTs are indeed well dispersed in the hydroxyapatite matrix. And to stress on one point, the carbon nanotubes have not been functionalized. They have the bonds of the CNT surface, they have not been broken, and they have not been functionalized to somehow interact with the hydroxyapatite surface. So that is the beauty of it, that carbon nanotube without any functionalization, it is getting dispersed into the matrix. So that is one of the beauty of the CNT dispersion in the hydroxyapatite matrix. This directly tells us that there is some affinity of the hydroxyapatite with the CNT. So in that particular case, we might achieve enhanced fracture toughness because of CNT addition. Now these compacts, or the three compacts, they have been spark plasma sintered. Spark plasma sintering is a mechanism where we pass a pulse DC current through the powder compact. So in this case, we can see we have a graphite die. This is nothing but the graphite punch or the graphite die. And in this case, we keep the powder, which is nothing but 1. So in this region, we keep the powder. Once we have the powder, it has been now compacted. So we compact the powder and we pass a pulse DC. And because of Joule heating, automatic there is some internal heat generation because of Joule heating. Once we are applying certain pulse DC current, and because of Joule heating, we get heat generation, and we compact the powder via punch, and then that results densification once we apply the pressure. So the temperatures can reach as high as in this particular case, we utilize temperatures of the order of 1100 degrees centigrade, pressures of up to 50 megapascals for a duration of 5 minutes. So the compaction can occur very rapidly. We are reaching the temperature of 1100 degrees centigrade. We can have heating rates as high as 100 to 200 degrees centigrade per minute, pressures to the order of 50 megapascal, and as we see, the sintering is completed within a time frame of approximately 5 minutes. So that is the beauty of spark plasma sintering. We create a localized heating along the powder particle surface, and after that it is followed by necking and rapid sintering because of the Joule heating. Simultaneously, we are applying certain pressure to it. So we can achieve densities very easily which are greater than 95%. And these are the spark plasma sintered samples. We can see the sample diameter is approximately 19 millimeter, and it has a thickness of approximately 5 millimeter. So we can see that hydroxyapatite is much more grayish, and with the addition of alumina, it is becoming much more whiter. And this blackish color is coming because of the graphene sheet which is kept on the top of hydroxyapatite powder, so that they don't really stick to the die. That is the part we can see here. The sample diameter is approximately 19 millimeter, and we can go as thick as 5 millimeter in the two cases. And as we see, the densities are pretty high, greater than 90%. And the same time, we can also say that we also want to say that porosity is one of the very critical components of estimating biocompatibility. because if the cells have to grow and somehow mechanically interlock, there should be enough porosity available for the cells to interlock themselves with the material, and they can extend their fibrous arms into the pores available, so they can also keep getting nutrients from outside. So that is the reason we can also say that we also need some porosity which available in the material to take care of the life of the cell. So in all the cases we have achieved the porosity levels approximately 5 to 10%. We can even control it using spark plasma sintering. In this particular case, we have densities to the order of greater than 90%, and those are listed out here. And once this pellet has been particular pellet has been synthesized, its X-ray diffraction spectrum was taken. In this case, we can see what is happening with the hydroxyapatite with alumina, and with carbon nanotube. So first of all, we do see the separate peaks of hydroxyapatite and those of alumina. So those part we can see very clearly. In some cases, we are also forming some minor phases of beta tricalcium phosphate, which is also being present here. But on the other hand, we don't see any complex phase formation. It has a very high crystallinity, as we see from the stronger or sharper peaks, that the crystallinity is very, very high. Secondly, we are not forming any complex phases between alumina, calcium aluminides or something like that. We are not forming at all. Also, we are retaining the crystal structure of alumina. It was alpha and it has remained alpha even after the sintering. There is no other formation of any gamma or any other metastable phase. So from XRD we can say that there is no formation of any complex phase, and all the initial phases they have been retained, though there is some formation of beta tricalcium phosphate. So this tells that this is happening because of the rapid processing time which is available for the spark plasma sintering, because our entire process gets completed in 5 minutes. We are heating the particular pellet, applying certain pressure, and then we are completing the process by holding it the dwell time of approximately 5 minutes for 50 megapascals. So we are able to complete the process in very short duration. That is the reason there is not enough time available for the phase transformation from, say, alpha alumina to gamma alumina, or formation of or chances of inducing any chemical reaction between hydroxyapatite and aluminum oxide. So there is no formation of calcium aluminides or any such complex entities. But one thing to note here is, in the XRD spectrum is, we don't see any CNT peaks, or we don't see any carbon peaks as well. So it means that we have to somehow say that, to verify that we are able to retain the carbon nanotube in order to tap the advantages which we can get from the CNT reinforcement. So in this case, we are not able to see any graphite or carbon nanotube peaks. So that is the reason we have done Raman spectroscopy, and from that we can clearly see that the graphitic peak is now retained in the HAA16C pellet. So this is for hydroxyapatite. We do see some hydroxyapatite peaks. This is again for hydroxyapatite with some alumina. So we are seeing mainly hydroxyapatite peaks because aluminum oxide peak is very, very feeble. And once we add carbon nanotube, we can see the similar D and G peaks. So the G peak is basically retained. That tells that the graphitic peaks of carbon nanotubes are intact even after spark plasma sintering. So spark plasma sintering is not inducing any damage to the carbon nanotube, and we are able to retain the carbon nanotube even after spark plasma sintering. So once we are able to retain the carbon nanotube, then we can expect enhanced mechanical properties, or enhanced fracture toughness, or enhanced tribological properties arising from the carbon nanotube. So this is a particular microstructure which shows that we have CNT dispersion. At the same time, we also do see some pull out. So in first case, we have hydroxyapatite with some alumina. So we can see that hydroxyapatite grains are out there, and we have nano aluminum oxide which was now dispersed in the hydroxyapatite grains. In the second case, we can also see there is some CNT pull out or carbon nanotube pull out, which is now in the hydroxyapatite and the aluminum oxide composite. So we do see that CNT pull out is occurring. That means that now some extra energy has to be supplied in order to break the carbon nanotube, because carbon nanotube has very high fracture strength. So there definitely we have to supply some extra energy in order to fracture carbon nanotubes or induce their pull out. So this pull out is telling two things, that first of all, CNTs are very well dispersed in the matrix. Secondly, it will also enhance its fracture toughness. So that those are the two things we can infer from this particular SEM image. So we are seeing that CNTs it is showing pullouts, and it is very well dispersed throughout the matrix. And it has also been shown by some researchers that CNTs, they also tend to spread out, and they enhance the fracture toughness by creating some CNT bridges, as we see here. So the CNT bridging also is very essential, because it won't let the two powder particles separate out so easily, and again their fracture will also induce some energy absorption for enhancement of the fracture toughness. So that is what CNT does by either diverting the crack itself. If a crack is generated, it will divert the crack, it will restrain two powder particles or two splats, and then it will provide its own energy in terms of basically preventing the separation or enhancing the fracture toughness. Additionally, it has been also observed that they can also improve the the wear resistance of the composite. So this is a particular profile which has been nano scratch. So we see that we have certain profile. So nano scratch has been done on a surface of hydroxyapatite out there, and from this we can see a certain depth which results. So this is the depth of hydroxyapatite only, and once we start adding some aluminum oxide onto it, we see this the much more roughness. The roughness part has increased drastically in the HAAA, or the hydroxyapatite, which has now been reinforced with aluminum oxide. So the roughness part has highly increased because we are adding sub-micron size aluminum oxide in a hydroxyapatite matrix. Additionally, we also have some induction of some carbon nanotube. So we can see the roughness part is also increasing. Initially with 5 nanometer roughness, we can go for very fine polishing, and as we add aluminum oxide, the surface roughness has now increased, the average surface roughness, and once we add much more carbon nanotube, one more reinforcement of carbon nanotube, the roughness has increased further. But more than that, once we are doing a nano scratch, we can see very nicely that the maximum scratch depth, which was so obvious in hydroxyapatite, it has now reduced very drastically, approximately 6 times. Further, once we are adding much more carbon nanotube to it, along with aluminum oxide, the maximum scratch depth has decreased further. It means now my wear should have gone to a very low level. Eventually, depending on the crack length and the crack depth, wear volume has been calculated. Once the wear volume has been calculated, from that we can see how much is the reduction in the wear volume, and that gives us the wear resistance improvement. So we can see with aluminum oxide addition, we are seeing improvement of approximately 13.5 times, and with further addition of only 1.68% of carbon nanotube, we are getting improvement of approximately 68.3 times. So that part we can very nicely say that once we are adding some aluminum oxide is a ceramic which has a very high hardness and very high fracture toughness. So it somehow restrains the damage which is imparted onto it, and it supports hydroxyapatite matrix. Hydroxyapatite matrix alone, it is not that though it is a ceramic, it does not have enough fracture toughness and hardness to support its integrity in terms of wear. So it basically wears out very quickly, and it shows a very high wear volume. But once we add some aluminum oxide to it, it is again a ceramic with higher hardness and higher fracture toughness. It somehow supports or resists further wear of the matrix, and that's how it has shown enhancement of approximately 13.5 times. Further, with the addition of carbon nanotube to it, if we start adding carbon nanotube to it, what happens? Carbon nanotube acts also as a lubricant. Graphene layers have been used as a lubricant. So somehow, because of its higher modulus, it has a higher fracture strength. Also, it also acts as a lubricant. So because of all combination of all the three, we also have an addition of aluminum oxide into it. Somehow it is increasing the wear resistance by more than 68 times. So we can see that change from HAA hydroxyapatite to that of addition of alumina, we are getting improvement of approximately 13.5 times. But once we start adding carbon nanotube to it, only 1.68% carbon nanotube, from 13.5 we are getting improvement of approximately 68.3 times. So approximately 5 times more improvement we are getting just by adding a little carbon nanotube into it. So that is the beauty of this particular composite, that we can get exceptional or very high, very better tribological properties once we add carbon nanotube and macron size alumina in the hydroxyapatite matrix. So to see what is CNT doing onto the hydroxyapatite, some computational modeling has been done. So in this particular case, ab initio molecular modeling has been utilized. Ab initio means we are utilizing only the electronic state of a particular material. Like hydroxyapatite is a complex C810 PO4 whole 6 OH whole twice. So in this case, we define the properties of a particular material or a particular component just by the electronic configuration. Like calcium will be defined by its electronic configuration of 1s2, 2s2, the way it goes, hydrogen by 1s1 and so on. So the only input required is the electronic configuration, and based on that Linux based software has been used, which is Siesta, which is called Spanish Initiative for Electronic Simulation with thousands of atoms. So in this case we can utilize many more number of atoms and see their interaction, how the interaction is happening using a Linux based software, and then the pseudo potentials are generated. In this particular case we assume the many electron problem as a single electron problem. So in this case we are avoiding so many interaction of so many electrons, and we are replacing that by interaction with only representing a particular or a complex material, complex atom with so many electrons by a single electron. So we assume that, say for oxygen we have 8 electrons, so we assume that all the 8 electrons, they are now being replaced by 1 electron which is behaving similarly as an average all 8 electrons will. So that is the reason we create some pseudo potentials by using those first principles, and then we have confirmed those positions by by doing a raw run of hydroxyapatite alone. So we confirm that the final coordinates of all the calcium, oxygen, phosphates, hydrogens, what we get in the structure, they match with the theoretical values of the hydroxyapatite crystal. So by that we have confirmed the pseudo potential that they are correct or not, and then we have created an interface of hydroxyapatite with carbon nanotube to see what is happening at the interface, why CNTs are getting so dispersed so nicely, and why they are inducing enhanced pressure toughness because of CNT addition. So an interface has been created which will tell us what is the interaction happening between the two. So this is how the crystal appears finally. This is what we have, the hydroxyapatite crystal, and these are the graphitic planes what we might expect in the carbon nanotube. So in this case we have all the atoms, calcium, phosphorus, oxygen and carbon and hydrogen. So that those all are appearing in the hydroxyapatite and the carbon nanotube interface, and since the interface between those two, it is not exactly matching, so a strain of 2.29% has been enforced, and a crystal of approximate size 9.6 by 9.6 by 14.58 angstrom cube has been created. And what we see here is that calcium, the hydroxyapatite has calcium atoms on its surface, those are here, and if we create certain planes, like this is the terminating plane of hydroxyapatite, so it has some surface calcium atoms, and these are the unperturbed graphitic layer. So we do see a very regular symmetry or the regular geometry of the carbon atoms on a particular plane. Those are unaffected, but as we start going near the interface, like plane C or plane B, which is exactly at the center, so we see that plane B and plane C, they start showing some effect or some distortion of the isosurface energy contours. It means there is some overlap of the electron density between calcium atoms and those of carbon atoms. So those interactions we can see out here, and we can see that there is some perturbation which is happening by distorting the isosurface energy contours. It means there is some overlap or some interaction happening between the electron cloud of calcium and that of a carbon. It means there is some sort of a bonding which is happening between the two, and that is resulting the automatic dispersion of carbon nanotube on the hydroxyapatite surface. So that is the beauty what we are seeing in this particular case, that we are able to see the dispersion, very nice dispersion of this carbon nanotube on the hydroxyapatite surface. So overall we could see that we have done ab initio molecular modeling. So we have input all the data is basically coming from the electronic configuration of calcium, of phosphorus, of oxygen, of carbon and hydrogen, and then an interface has been created between them, and since the interface can't match exactly 001 of hydroxyapatite and 001 of CNT can't match, so a strain had to be introduced, and this strain will allow the overall crystal to match perfectly. And from that there are certain planes which are unaffected planes, those are plane A and plane D. So those are remain unaffected, they are much far apart from the interface, but as soon as we start coming near the interface, we see some overlapping of the electron cloud or the isosurface energy is now getting perturbed because of the interference from the surface calcium atoms, and that is the reason that it shows some affinity towards the carbon nanotube, and then we see a nice distribution of carbon nanotube with hydroxyapatite. And once we have confirmed the nice interaction which is happening between the CNTs and that of hydroxyapatite, we also want to make sure what is happening in terms of their cytocompatibility. So a very nice sample has been obtained, that we have taken a hydroxyapatite control sample. It is a negative control, so we can see that L929 cells or the mice fibroblasts have been growing very nicely on the surface of hydroxyapatite, which is a control sample, and the same thing we are seeing in the hydroxyapatite. As we add alumina into it, we can see the density has gone approximately similar, and also with the addition of carbon nanotube we are seeing approximately similar density or higher density. So this tells directly that we are not affecting or we are not inducing any toxicity by adding aluminum oxide or by adding carbon nanotube into the matrix. So this case we can see very nicely in the hydroxyapatite we have nice flow of spread of all the cells, fibroblasts, and there are a couple of things which we can note here is, first of all, we do see some formation of cells and also some which are spread out, and there are some cells which are still globular in nature. So in this case we can see some cells which are much more globular in nature and some cells which are still spreading out. So generation of this kind of morphology is very, very common, that we do see some cells which remain globular and some basically spread out. The spreading of cells is limited to once they find some friendlier surface, they tend to increase their surface area, because that helps them to interact with the surface nicely, because once we have higher surface area and then they can interact to a larger extent with the underlying material. That is the reason they tend to spread, and if they do not find the surface to be friendly, they remain globular, because now they have the interacting surface area is very, very low, because for a sphere and for a plane the overall contact area will be just like a point. So in those cases, once they remain globular, they do not find the surface to be friendly enough, or when the surface is not that cytocompatible, it tends to remain globular. But in the other cases we have seen similar some globular cells as well, but most of the cells are spreading out and they are enhancing in their lengths. So it means that the cells are not only adhering, they are also growing. So we can see three things: the surface is cytocompatible, cells are finding the surface cytocompatible, and because of that they are spreading, and once they are spreading out, they are also tending to grow further. So unhindered growth has been also observed in this particular cases. So we do see some for a little higher magnification, we do see some globular cells which are out there, and we also see some spread out cells. So we can see most of the cells, they are now spread out. So in this case this is a control sample and this is one with the CNT. So we can see that cells are basically spreading out like this, they are extending their arms, and their overall surface area has been now enhanced because of this, and that is what we are able to see in this particular case. So that tells that cytocompatibility has been retained even after the reinforcement with the carbon nanotube. So in this case we can see that CNTs, they are not only enhancing the fracture toughness, or they are not enhancing the tribological properties, but they also assist in the apatite precipitation on its surface. So in this case we can see we have the cells which are basically like this, and then we also have some carbon nanotube, and over that we are seeing some precipitation of apatite on its surface, and that part has also been confirmed by a couple of researchers such as Laura and Haddon's group. They do see some barbed wire kind of a structure, that they have CNT, and over that they see very nice precipitated apatite needles on the surface of carbon nanotubes, and the same structure is also observed in this particular case, that we have carbon nanotubes and they have very nice dispersion of or precipitation of apatite on its surface. So one thing is very clear, because of higher surface area available for the carbon nanotube, it is somehow assisting the precipitation of apatite. And why the apatite precipitation is very, very important, because now that is what required for the bone growth. So once we have available CNT surface with a particular implant material, it will also assist the precipitation of apatite or the generation of new bone. So there are many advantages which are associated with carbon nanotube, that apart from improving the tribological properties dramatically, it is also assisting the apatite precipitation. So it confirms that once CNTs, if they are entrapped into a particular matrix such as hydroxyapatite, they are not being toxic anymore. So in this particular case, we can say very strongly that we have CNTs and they are somehow encouraging the precipitation of apatite on its surface. So in this particular case, we also see some CNTs, they are totally covered with apatite. Had they been toxic, they won't allow the precipitation of apatite, they will just kill the cells which are already there. So in this particular case, we have osteoblast, and then those osteoblasts, they are growing very nicely because we also see some precipitation of apatite crystals on the carbon nanotube surface. So that part is very clear, and we don't see any dead cells on nearby its vicinity. Further, there has been MTT assay, so a quantification of them of the viable cells has been done. So in one case we see hydroxyapatite, which is approximately, control sample is taken as 100, and then we have some hydroxyapatite. Because of the porosity, we can also see that hydroxyapatite is approximately similar to that of the control sample, whereas for hydroxyapatite with alumina, it is showing lower percentage of viable cell. That might be happening because aluminum oxide is bioinert in nature. So that part we can say that because of the inertness of the aluminum oxide, it is somehow reducing the viability or the cell viability which is available. At the same time, the particular structure was highly dense. Its density was 95 in comparison to the other two. For hydroxyapatite, the density was around 91%. For the with alumina, it was approximately 95%. Then again with CNT, it is 91%. So somehow porosity is also playing a role, that the cells are not getting comfortable enough in the highly dense region, that is hydroxyapatite with alumina in it, and this results are for the 3 days. And we do see that the similar nature is also being rendered by the hydroxyapatite with some alumina and carbon nanotube. So in this case also, because of higher porosity, we can say that the cells are finding themselves comfortable. Had there been some toxicity associated with carbon nanotube, we should see a decrease in the cell viability. But now this is now much more in comparative to what we are observing for the hydroxyapatite alone. Later on, definitely we can see the hydroxyapatite alone, the cell viability has gone drastically up. The control sample is generally dense, and with enhanced porosity, because it is 91% dense, we do see much enhancement in the cell viability. It means porosity also is one of the very critical features or parameters in terms of dictating the cell growth. Further, with addition of aluminum oxide, it is again very dense. Alumina is bioinert in nature, so it is always showing a reduced cell response in comparison to the other two pellets. Further, for hydroxyapatite with some carbon nanotube addition, this now catches up with the standard approximately 98-99%, and then somehow it is catching up with what was available for the dense hydroxyapatite. So this tells very clearly that the sample with some CNT in it, with some alumina and CNT in it, is in no way inferior in terms of cytocompatibility. At the same time, it is inducing tribological resistance of more than 65 times. So that is the beauty of it, that we are able to attain similar cytocompatibility with much enhanced tribological resistance once we add some carbon nanotube into the matrix. And that thing all is achieving, we are able to achieve that we have hydroxyapatite, we have hardness of over approximately 4 gigapascals. Once we add some alumina, we see much enhancement in the hardness and much enhancement in the fracture toughness as well. But it now compares lesser in terms of cytocompatibility, but it is definitely superior in terms of the mechanical properties as well as the tribological properties. So in this case, we are achieving a improvement in the fracture toughness or the tribological properties, or the we are observing enhanced wear resistance, and the wear volume was decreased by 13.5 times with addition of alumina. So that is the advantage. With hydroxyapatite, we have certain properties, hardness is 4.0 gigapascals, fracture toughness 1.18 megapascals root meter, and once we add aluminum oxide to it, properties are somehow dramatically enhanced. The hardness increases to 6.1, approximately 50% improvement, and we also see improvement in the fracture toughness. approximately again approximately 90, around 80-90% improvement in the fracture toughness we are getting automatically with the aluminum oxide addition. But as soon as we add even little amount of carbon nanotube, 1.6 weight%, the hardness is somehow increased by approximately 10%, and we don't care much about the hardness, because we are able to achieve the similar cytocompatibility as that of a standard hydroxyapatite, of a dense hydroxyapatite. So that manner we are able to achieve hardness similar to that what we can get for the hydroxyapatite, but now the fracture toughness, so that is what the limiting factor for hydroxyapatite application. We can achieve fracture toughness improvement of more than 100%. So we are approximately 1.3, 1.4. The approximate improvement in the fracture toughness is approximately 2.3 times, or more than 100% improvement. So that is the criticality that we can achieve or we can attain by the carbon nanotube addition in the hydroxyapatite matrix. So that is the overall philosophy of using alumina as well as carbon nanotube in terms of improving the hardness, fracture toughness, maintaining the cytocompatibility, and improving the tribological properties by more than 65 times. So that is the overall theme of this particular spark plug centered samples. So first of all, the hydroxyapatite, which was reinforced with aluminum oxide and carbon nanotube, it was successfully spark plug centered, because being able to do that also is very critical, because the sintering temperatures for all of them are very different. For hydroxyapatite it is different, for aluminum oxide it is different, for CNT it is different. So once we are combining all of them, it becomes very difficult to maintain a particular parameter which can center all of them together and in a very nicely uniformly dispersed manner. Once we are able to disperse the CNTs, disperse the aluminum oxide in hydroxyapatite matrix, we can attain uniform properties. So that is one of the key essential or the essential parts of spark plug centering, that we are able to achieve a nicely dense compact or a pellet of hydroxyapatite with aluminum oxide and CNT, and at the same time we are also maintaining certain porosity into it, and that is assisting the ingrowth of cells. And secondly, we are also able to improve the fracture toughness by more than 2 times. So once we are adding some carbon nanotube, we can increase its fracture toughness from 1.18 to approximately 2.72. It is approximately 2.3 times improvement, and that all is happening without deteriorating the cytocompatibility. So that is achievement in itself, that we are able to achieve excellent interfacial bonding with unhindered biocompatibility of hydroxyapatite, which is now reinforced with aluminum oxide and carbon nanotube. So this particular material can serve as a potential implant material. That is the beauty of this overall structure. So in this particular lecture, we learnt about what is hydroxyapatite, and it has a chemical structure, chemical composition similar to that of bone and teeth. And then why do we add aluminum oxide? Because it has much superior hardness, and it also has much better fracture toughness. So it can eventually lead to enhanced tribological properties. But the problem with that is it is bioinert in nature. So that is the reason we can also add carbon nanotube to it. Carbon nanotube, they are bioactive in nature, and they lead to apatite precipitation on its surface. So somehow they can enhance the mechanical properties without deteriorating the cytocompatible properties. So it was followed by computational modeling as well, that we want to see how the CNTs are dispersing on the hydroxyapatite surface, because we saw the dispersion of CNT without any functionalization on the hydroxyapatite surface. And then this composite was spark plasma centered. After spark plasma centering, the properties came out to be much more superior with the aluminum oxide addition. The hardness was improved by more than 50%, fracture toughness almost doubled, and with further addition of carbon nanotube, we saw the hardness was basically approximately similar, 10% improvement, but fracture toughness improved by more than 2 times. And it was followed again by the tribological properties, and in that we see that aluminum oxide can improve the can reduce the wear volume by more than 13 times, because it has very high hardness, it has very high fracture toughness, so it somehow improves the tribological properties. But further addition of carbon nanotube can also act as a lubricant in addition to the reinforcement which is being provided by the aluminum oxide. So the overall property was increased by more than 65 times. So this overall combination of aluminum oxide and CNT acts synergistically in the hydroxyapatite matrix to improve its fracture toughness, but without deteriorating the cytocompatibility. So with this, I basically will close my lecture. Thank you.